Okay, here we go. Chapter 1, Limits Review. We're going to do a quick review through the limits chapter that we learned last year in Honors Pre-Calculus. Here we go. The limit of this function as x approaches 0. We're going to look as x is approaching 0. It's approaching from both the right and the left side. As x is approaching 0 this way, we're going to look at the height of the graph. The height of the graph, right, is the y. So as x is approaching 0 from the right, look what the height of the graph, or the y value of the graph, is doing. It is approaching 1. And then if we look at this graph from the left, as x is approaching 0 from the left, what's the height of the graph doing? Well, the height of the graph, which corresponds with the y value, is also approaching 1. So the limit of this function as x is approaching 0 is 1. Now I want you to notice that if you were asked for what's the value of this function when x is equal to 0, so what's f of 0, we would look at this and go, oh, there's no value, right? There's no value when x is equal to 0 for this function. We would say it does not exist, or we would say undefined. There is no value there. So just note that the limit is asking us something different than the value of the function at a certain x. All right, and here we go. We're looking at the limit of this function as x is approaching 2. So when we approach from the right, as x is approaching 2 from the right, we're looking at the height of the graph and what it's doing. It is decreasing and it's heading towards 3. And then when we look at as we're approaching 2 from the left, we're looking at the height of the graph, or the y value, and we see that it's increasing and it is also approaching 3. So the limit of this function as x is approaching 2 is equal to 3. Now, just to compare, if the problem also asked you to find the value of the function when x is exactly equal to 2, so f of 2, we would note that although the limit is equal to 3, the value is actually this dot up here. And so that would equal 5. All right, and when we're looking at this, the limit of f of x as x is approaching 0, as we're coming in from the right, we're checking out the height of the graph, of the y value, and it is zooming in to 0. Same thing as x is approaching 0 from the left. We notice that the height of the graph is increasing, and it's heading towards 0. So the limit of this function as x is approaching 0 is 0. It just so happens, if we can take away all these arrows and just look at the value of this function when x is exactly equal to 0 is also 0. So sometimes the limit and the f of x will actually match up and be the same. And we'll learn more about what that means. Well, we'll remind ourselves because we know what that means in just a second. So let's look at this. The limit of this function as x approaches 1, as we're looking at this graph, as x is approaching 1 from the right, we see that the height of the graph is increasing and heading towards 4. And then as we look at the graph from the left, as x is approaching 1 from the left, we see that the height of the graph there is approaching 2. And so there's not a consensus here, right? We're not approaching the same thing from the left and the right. Therefore, we say that the limit does not exist. And I always say a2dv, and I don't think that's a technical term, but approaches to different values. Sometimes you'll have to state why the limit doesn't exist. You can write it out in words if you'd like, especially for someone that doesn't know what a2dv means. Another way that the limit doesn't exist is when you're looking at a function like this, the function sine of 1 over x, as x is approaching 0, it is oscillating back and forth. It cannot make up its mind where to land, somewhere in between 1 and -1, right? So let's see. Oops. Let me see where hold on a second. I left my marker over here. Okay. So let's see what's behind. There you go. It's oscillating, and so when a graph cannot make up its mind, the height of the graph, so the y value can't make up its mind as x is approaching from both the right and the left, and it just keeps oscillating, we say that the limit does not exist, and we would write that it is oscillating as the reason. All right, another way a limit won't exist is if we're approaching an x value and our height shoots off to infinity. So our y shoots off to infinity. So as we're approaching x from the right, we see that our y values are increasing, and they are just shooting up, right? They'll go, well, they're not going to curve the way I did. They're going to just go alongside that asymptote. And so from the left, as x is approaching 1 from the left, the y values of those x's as they're approaching 1 are decreasing and heading off to negative infinity. So for this, we would say that the limit does not exist, and you could say plus or minus infinity because it's doing both. Okay, so limits fail to exist for 3 reasons, right? It can approach 2 different values, approaches 2 different values from both sides, or it can shoot off to infinity, negative infinity, or both positive and negative infinity, or it oscillates. Those are the 3 ways that a limit will not exist. All right, finding the limit numerically. So there are 3 ways to find the limit: graphically, which we just did, numerically, and then analytically. So let's look at numerically and just remind ourselves what we do when they ask us, whoever they are, to find the limit of something numerically. First, we're going to make a table. And before I make a table, I think about a number line. So I popped up a number line here. I see x is approaching 2. And I know I want to make a table where I approach 2 from both the right and from the left. And I could choose to approach 2 from the right, going 5, 4, 3, 2. But that's not going to help me when I make a table and try to find the limit numerically. I need to get super, super close to 2. So from the right, super, super close to 2 would look like 2.1. And super, super close to 2 from the left might look like 1.9. And then we just get closer and closer from there. So I'll show you how I set up the x, starting with, from the right, 2.1, and then getting closer with 2.01, 2.001. You don't need to go crazy with that. 3 is enough. And then with the 1.9, getting closer and closer to 2 from the left, 1.99, 1.999. You pick up your calculator, you plug it into the function, and you get the values both from the right and from the left. They are approaching the answer, which is -4. Now, we've seen the movie, we know how it ends. We do know that you can just plug 2 in and get the limit of -4. But sometimes you're going to look at a function where the only way to find the limit is numerically. And so it's really important to understand this method for finding the limit. Okay, and then let's go to analytically, because obviously in the last one, if someone asked us to find the limit analytically, we would just plug 2 in, right, into every single x, and we'd solve and get -4, and we'd be done. That would be the limit. And so, no, they need to give us ones that are not that easy, right? So what's the problem here? When I don't know why that's doing that. Okay, there we go. When I see that they want me to find the limit of this function as x approaches 5, I'm like, great. Couldn't you have picked a different number, right? If I plug 5 in, it's going to really mess up this whole thing because it's going to give me a 0 in the denominator, and I can't have that. So I can't use direct substitution when I'm finding the limit analytically when there's an issue in the denominator. So that's the first place we look, is the denominator, and we're looking at what number we're plugging in there. If there's a problem, then we've got to do some algebra before we can do direct substitution. So here we go. I look at the numerator. We can factor that numerator, right? Now, I like to write the limit part of the problem as I proceed, because otherwise I might forget I'm even in a limit problem and get the answer wrong. So I'm going to factor the top. Some people call this unfoiling. If that helps you to think of, you can think of it that way. I need 2 numbers multiply together equal -30, but add to equal a +1. So that it's going to give me a +6 and a -5. And I'm like, yay, this is how it should turn out. The problem should go away. It cancels out, and now I can use direct substitution and plug 5 in. 5 + 6 is 11, and that is the answer to my limit problem. Sometimes we're also going to see, well, first of all, let's notice that if we're taking the limit of this function as x approaches 3, we're going to have an issue in the denominator. Do you guys agree with that? I'm just checking the time. Yeah, so we need to get rid of it, and gosh darn it, look at the top, look at the numerator, I can't factor. And so what I'm going to do is multiply by the conjugate and get things kind of mixed up, so maybe something good will happen. So the conjugate of a binomial, right, this is a binomial, we have two terms. A conjugate is you just rewrite the binomial, but instead of a minus, we're going to put a plus in there. And of course, because we're not in an equation, we can't just do something to one side and then balance it by doing it to the other. We're not in an equation. So the only thing we're allowed to do is if we do something to the numerator, we better do the same thing to the denominator, right? Because then that means we're just multiplying by 1 in disguise. So here we go. I'm going to remind myself that I'm in a limit problem by rewriting this part. And then I know when I multiply a binomial times its conjugate, the cool thing is that the two middle terms cancel out. So root x plus 1 times root x plus 1 is x plus 1. Negative 2 times 2 is negative 4. I have learned in all my years of math that when I multiply the numerator and the denominator by a conjugate, I do not distribute I do not distribute the denominator. I never get rewarded for that. In fact, you get punished. All right, here we go. 1 minus 4 is negative 3, so I'm going to rewrite this, if that's okay with you, as x minus 3, and then it's all good, right? X minus 3 cancels out with x minus 3. What am I left with on the top? Let's rewrite so we know what we've got left. When everything cancels out, sometimes people space out and put a 0 up there. You would never do that, right? I didn't think so. So we're going to put a 1 up there because that's actually what's left when something cancels out. Think if I had 5 over 5 and they canceled out, what do I have left? 1. All right, now I can go ahead and do direct substitution. I'm going to plug in the 3 in for the x, and so I'll get what? 1 over root 4, which is 2. 2 plus 2 is 4, and that's my limit. So we've learned two methods for when we're finding the limit analytically, 1 factoring and 2 multiplying by the conjugate. And then, of course, we've got our special trig limits. The limit of sine x over x as x approaches 0 is 1, and the limit of 1 minus cosine x over x as x approaches 0 is 0. I know that some of my pre-calc kids would remind me, because I like to tell people like goofy ways to remember things, and they said, well, you know, this one's easy. I see a 1 in the sine, and that's a 1. I see a 0 in the cosine, that's a 0. All right, so you can thank my students if you haven't already thought of that already. So we look at something like this. We know that, bummer, if we plug 0 into our denominator, we're in trouble already. And we can't use multiplying by the conjugate. We can't factor. We can't simplify. So we've got to count on using, I'm going to take away these blue things because it kind of messes us up. We want to rearrange tan squared x over x by using our trig identities so that we can use one of these special trig limits. So here we go. We know that tan squared x is the same thing as sine squared x over cosine squared x all over x. So let's stop here real quickly. If I have a fraction within a fraction, I know that the numerator in both the numerator and the denominator stays the same. So see the sine squared x, that stays there. See this x in the denominator, that's in the numerator of the denominator, that stays there. The denominator of the numerator actually gets kicked down to the denominator. Now, if that doesn't make sense, you can always do, oh gosh, I hate to say Kentucky Fried Chicken, but that's the keep, flip, change with any fraction, right? We could do the sine squared x over cosine squared x divided by x. That's what this, man, I'm using too much blue. That's what this part says. It's really a division problem, right? And so keep says keep the first fraction the same. Flip says flip the second fraction. So now it's not a fraction, I get it. So we're going to do x over 1, and then we can flip it. And then change says the division sign changes to multiplication. So we'd end up with the same thing. I just prefer to do it the first way, but you can always do the division to the side if you need to. All right, and nothing looks exactly like these special trig limits, except for I see that we're going to end up with this, right? Because I can go ahead and break this up, and that's what I'm going to do. My goal is to use sine x over x, so I'm just going to rearrange what I have. So I have sine x over x. All right, use that. What's left that I haven't used? Well, there's another sine x, right? I already used the x, and then there's just a cosine squared x on the bottom. Then I'm going to remind myself that when I see something like this, I can actually split it into two limit problems. So I can have the limit of sine x over x as x approaches 0 times the limit of sine x over cosine squared x as x approaches 0. I already know that sine x over x is equal to 1. The limit is as x approaches 0, so that's a 1. And then the limit of sine x over cosine squared x as x approaches 0. Sine of 0 is 0, right? And then cosine of 0 is 1. And you multiply those two together, you get 0. Okay. All right, so then this just goes over some different ways to go ahead and find the limit analytically when there is a problem in the denominator. Once again, sometimes students decide, even if there's not a problem, that they're going to factor and do so. If there's not an issue in the denominator, just do direct substitution. All right, one-sided limits, here we go. When we see this sign right here, a negative in the exponent spot, that says the limit as x approaches 0 from the left. So if we can remember that from last year, that's from the left. And then when we see the plus in the exponent spot, that is from the right. Let's see what I did behind this. Let me put this down and see. What did I do? Okay, I graphed it. That was nice of me. I wanted to cut the time down of this video, so I graphed it ahead of time on Desmos. And so we can see coming from the left, let me choose a different color. So coming from the left, as x is approaching 0 from the left, we have a value here of, well, that looks like a -1, or is it a -2? Okay, hold on just a second. Okay, so obviously, even though we don't have markings, that's not a -1, and it's a -2. I just had to pause it and do some math in my head, so sorry about that. So we've got, from the left, the limit is -2, and then from the right, as x is approaching 0 from the right, we are approaching not -2. It's been a long day. All right, we're approaching 2 from the right. And so if we wanted to know what's the limit of this function as x is approaching 0, obviously, since we're approaching two different values from the right and the left, the function's approaching two different values from the right and the left, the limit will not exist, right, because it approaches two different values. But the one-sided limits do exist. So one-sided limits are cool to get some info that we couldn't get if we were looking at it all together. All right, piecewise function, when we have this first part, I wrote in from the left because when we're looking at x is less than or equal to something, we're coming from the left. And then this second part, as we're looking at x is greater than -3, that means we're coming from the right. And so what I did real quickly, and you can pause this if you need to, is I made a table from the left and I made a table from the right. Now, you see that I did this, gosh, I don't know if I can get the turquoise back up, but I did this turquoise box around when x is equal to -3. I realize that there's not an equal sign here, that just says x is greater than -3, but I always teach my students to put a box around there, so that's where we put the open circle when we graph. So let's just graph that part first. I'm going to graph the from the right first, and if I were just, once again, you can pause and see how I got those points, but I wanted to save time and just do that before we did the video. So if we did -1, 1, we've got that, and -2, -1. There we go, and -3, 1, 2, 3, -3. And I'm not going to do a closed circle, I'm just going to do an open circle. So I'm going to go ahead and connect those and shoot that off. All right, so that's from the right. And then from the left, I'm going to go ahead and I notice that at -3, -3, I get to fill in this open circle. The open circle is saying that's the function's undefined. For that part of it when x is equal to -3, but the first part of the piecewise, the first function in the piecewise function had a value when x is equal to -3, which is cool. 1, 2, 3, 4, -4, 0, that's my next point, and -5, 1, that's my next point. So here we've got, oh, not drawn to scale. Anyway, so what we have here is we have a piecewise function where the limit from the right and the limit from the left is both the same. It's both -3, and so the limit of this whole piecewise function as x approaches -3 is also -3. All right. So if both sides, your right-sided limit and your left-sided limit are the same, then the limit at that particular point C exists. Let's see what we have behind here. We have a piecewise function here where the limit does not exist at 2, right? Because we're approaching from the right and the left, 2 different values. We do have a limit, a right-sided limit and a left-sided limit, it's just they're not the same. And then the second example is if we look at, let's say, the limit as x is approaching 1, the limit does exist because the right-sided limit as x is approaching 1 is 1, and the left-sided limit as x is approaching 1 is 1. I hate when the x and the y values match up. All right, but that's that. All right, so continuity. Continuity is a really important idea. When we differentiate, we talk about continuity in relationship to differentiation, so it's important to understand what continuity means. And so we can just say the informal definition is like, yeah, you draw a curve or a line and you never pick up your pencil, right? There's no holes, no gaps, no asymptotes. This is a great informal definition, but it doesn't help us out as much as the formal definition. So the first thing is if you're going to have continuity at C. So we're looking at continuity at a certain point C, and then we'll talk about everywhere continuous after that. But we're just talking about at a certain point C. So you can see here, there's the C, there's the C, there's the C. So the first thing that we have to have is f of C has to exist. Unfortunately, in our first picture, right, f of C is not defined. It doesn't exist. Usually, I see f of C is defined. So in this slide that I found, it says exists. I'm not going to be picky. And then the second condition that has to be met is the limit of f of x has to exist. So here, when we look at the second picture, we do have a value for when x is equal to c. So f of c does exist, but gosh darn it, the limit doesn't exist. So therefore, it's not continuous. And then the third condition that has to be met is they have to be the same. So when we look at this third picture, it shows us how, well, wait a minute, the first condition is met, right? We have a value, there's f of c. The second condition is met. There is a limit coming from the right and coming from the left. It's approaching the same value, but gosh darn it, those limits and the limit and the f of x is not the same. And so those three things have to exist. Once again, I would spend more time on this, but this is a quick review. I know that on my pre-calc test that I've given, students have had to memorize that, but I think it's pretty intuitive. All right, and so then when we talk about everywhere continuous, we're talking about if a complete function is continuous, like the function y equals x squared, that's everywhere continuous. There are no holes, there are no gaps, there are no asymptotes. And all these three, sorry, I'm going to pause for my, oh, it stopped. So all these three conditions exist. And if you want to talk about continuous on an open interval from A to B, that's also something that you can have discussions on continuity. All right, so let's talk about when a function is not continuous, then that means that there's a discontinuity, right? If it's not continuous at a point C, then there's a discontinuity there. There are two types of discontinuities. There's removable and there's non-removable. Go ahead and pause this screen and you can read it. And I'm just going to go ahead and go to the next page and do an example. All right, so this is something similar to test problems that I know that I gave in pre-calc and honors pre-calc, so let's make sure we remember how to do this. Find all discontinuities and label them removable or non-removable. So discontinuities are going to occur when we have issues in the denominator. And so when I look at here, I know there's going to be an issue because I have x's in the denominator. Well, that's That's not always true, right? But it is a warning sign. And so what I want to do is factor the denominator and see if I have any problems there. And so let's go ahead and we're going to factor the denominator, and we'll think of two numbers that multiply to equal 15, positive 15, but add to equal negative 8. So that's negative 5 and negative 3. So right away I'm like, okay, I'm going to have issues when x is equal to 5 and when x is equal to 3. I will have discontinuities there. All right, so let's see what kind of discontinuities I have. So I'm going to go ahead and rewrite the numerator, and I realize I have the difference of two squares here. So I'm going to factor those. It's x plus 5, x minus 5. So here we go. We can see that although there's a discontinuity at x equals 5, we can cancel that out. Okay. So we've got a removable at x equals 5, there's a removable discontinuity. That means there's going to be a hole there in the graph. And then this x minus 3, there's no removing it. And so at x equals 3, right, because that's where the denominator will be equal to 0, we're going to have an issue there. That's a non-removable discontinuity. And that means there's going to be an asymptote there. Other non-removable discontinuities are just gaps, right? But the holes are the removable ones. Okay, let's see what else we have. Yay, the only thing left in Chapter 1 to review are limits at infinity, and I'm going to go ahead and direct you to watch, if you need a review on that, the 11.4 limits at infinity video that I have linked to the blog. I think it's a 20-minute video. Feel free to just slide through. When you find limits at infinity, you do need to show your work. Obviously, you can use the shortcut rules that we learned in Algebra 2 Trig, but we're in calculus now, so you need to show your work. All right, thanks for joining me. And if you have any questions, I can answer them in class, and I'll see you in class.